All right. Happy Thursday. Now, Thursday, week 7. This is the last of our new material. I have it. My glasses are distracting me. There's a smudge. Today is the last of the new material. On Tuesday, we will have drop-in office hours. Thinking 5:30 to 6:30 will be our hour. I know I normally do 5 to 6, but we've kind of made it a habit to come in at 5:30. So 5:30 to 6:30 on Tuesday, that'll be our drop-in office hours. That way you can ask me any questions about like the test review or maybe last minute project questions because it is due Tuesday. Reminding you that since the test is open for 3 days, Tuesday, Wednesday, Thursday, I don't usually say this, but you might want to prioritize your project. Prioritize the project, maybe take the test on Wednesday or Thursday, get that project in. And once your project's in, you need to comment on at least three of your classmates' projects. So it'll be in a forum, and I will not allow any new posts after Tuesday night. No late projects are allowed. So usually it's more like 3:34 a.m. on Wednesday morning that I stop things, but don't do that. Don't, so at after Tuesday night, I will make it so you can't post anything else, but you can still comment. So comment on at least 3 of your classmates' projects, and they need to be meaningful comments. So don't just say, "Hey, this is really pretty, nice job." I want you to ask a question about the project or make a comment about something you liked about the project. Make the comment meaningful. It's almost like when somebody sends you a text that's just a thumbs up or just an okay and how annoyed you are that it's not a real text that made you pick up your phone and look at it. You want them to open it up and see that you actually looked at their project. You want to show me that you actually reviewed it. And if you do more than 3 in order to make sure everybody gets comments, that'd be nice. I really, it makes me sad when I go in there and there's somebody's project that doesn't have any comments on it. So, you know, be mindful of that just to kind of be good classmates and make sure that everybody gets at least one comment. So I'm real excited. There's so many great ideas. I'm so excited to see what everybody has. I make a point of not spoiling what anybody's topics are so that y'all will be surprised when you see them. There's some really great topics out there. I'm so excited. So that's that. Today we are going to finish section 10.2 and do section 10.3. 10.2 will build on what we did in 9.2 and 8.1, and 10.3 will build on what we did in 9.1 and 8.2. So 10.2 is about proportions, and 10.3 is about means. So when we get to the end of 10.2, I'll tell you to put all of that information in your pocket. We'll do 10.3, and then kind of like I did with confidence intervals, I have a comparison at the very end so you can see what things look like. I have a couple of slides comparing things. There's also a really good handout comparing them. And actually, before I jump into this, because I might forget, I want to go to I don't know if you've all have looked at week 8 yet. You've probably been focused on week 7. Years ago, I made a PowerPoint right here, a final review PowerPoint. Most people print this out for their last test because what I did, and it's not going to make a ton of sense until you learn about hypothesis testing, but on the first page, I put all of the information about confidence intervals, what you need, what information you need, or what the formulas are, what the calculator function is. I do that on both the mean and the proportion. And then I do the same thing with hypothesis testing. I tell you what the calculator functions are, and I tell you what, give you all the formulas and everything. So this is a really good PowerPoint to print. It's just found in the week 8 material, and it's at the bottom. And that is really good for notes on your test. There's also a handout here that compares the 2 hypothesis tests. And there's a handout here that compares the confidence intervals. So these are all good handouts if you want to print them and use them for your test. It's almost all the information you need in order to do the test itself. Even though chapter 8 is in there, but the thing about chapter 8 is it's really kind of chapter 8 is just like the foundational material for 9 and 10. So chapter 8 kind of doesn't fully stand on its own, just little bits and pieces do. So if you have 9 and 10 down, you probably are good with 8 as well. Okay, so we're going to do population proportion hypothesis testing. And I'm not actually going to use the binomial probability distribution because I just want you to use your calculator function. And the calculator function is more accurate, so I'm not even going to do the binomial probability distribution. If you want to do that, you can read it in your book, but I would rather give you, I would rather it be like a quick, what is the word I'm looking for? I'm efficient. I would rather make you efficient workers than give you a whole bunch of extra information. So that's what we're going to do. And then we're going to talk about mean. Once again, we're going to be working with t-values, and we're going to be doing hypothesis testing about the mean with the t-values. So we've already kind of touched on what we're doing. We're just going to do the math to tell you how to do it. It's good. This is good stuff. All right, let's start. Okay, we're in 10.2 still. So remember point estimates. Remember, in order to get our p-hat, you take the number of successes and divide it by your sample size. So we're still doing that for our p-hat. So X is the number of individuals with a characteristic or a success. N is your sample size. So this is just a reminder. I think I finally reached when I first started teaching, some people knew what the string around the finger meant, and now very few people know what that means. You guys know what that means? It's like, I think that the reason people used to tie a string around their finger to remember things, and I think that it was basically like making that connection. If I'm thinking about something while I'm tying the string around my finger, then every time I look at the string around my finger, I'm gonna remember that thing. So it's like a connection thing. And that's what that's about. My little tangent there. All right. Another reminder is that when we are using sampling distributions, the standard deviation, the new standard deviation or standard error is this formula right here. These requirements need to be met right here. These requirements need to be met. Simple random sample. Our NP times 1 minus P is greater than or equal to 10. What it means that they're independent of each other means that our sample size is less than or equal to 10%. Uh-oh, we do 5%. 5% of the population. So now on your test, when it opens on Tuesday, on your test, there's going to be one proportion problem and one mean problem where you are conducting a hypothesis test, and I want you to show me every step on your paper. So this is important. Listen to this. It says to clearly show every step of your hypothesis test in your notes. I want you to show, I want you to show this on your paper for your proportion. I want you to state whether it's a simple random sample. If it isn't, no big deal, still do the math. State whether it says it's randomly selected, random sample. Do the NP times 1 minus P and make sure it's greater than or equal to 10, and state that your sample is less than 5% of the population. State these things because these are part of a hypothesis test. Then it is okay with me if you use your calculator function, which I'm going to teach you, but you need to write down that you use your calculator function and what you put in there. I want you to clearly show me every step. I want to show me the setup of the hypothesis and show me every little step. So that's what I'm looking for on those two problems. So the proportion problem, show me NP times 1 minus P greater than equal to 10. Tell me whether or not it states it's random, and show me that it's less than 5% of the population. All right. There we go. As I said, I don't want to surprise you on the test. I want you to know what's there. Okay. So when you are setting up a hypothesis test, you need to know if you have a two-tailed, a left-tailed, or a right-tailed. Our P naught, remember if we have a sub-zero, that's not. P naught is the population proportion that they give you. It's what we are assuming our population proportion is until we have evidence to show us otherwise. So that's why this says P naught. Your calculator will also say P naught. So that is our assumption. The P naught is we are assuming this is true until we show it's not. So this right here is P naught. Okay. So we talked about what left-tailed and right-tailed and two-tailed were the other day. So two-tailed is if it says the word different. Left-tailed is if the verbiage implies less than. Right-tailed is if the verbiage implies greater than. So it could say more than, or it could say has increased, but the implication is greater than. So these are what you're looking for in your problem. Okay. So it says to select the level of significance based on your seriousness of making a type 1 error. So the seriousness of making a type 1 error, basically what that means is if this is something super critical, like discriminating against women in the workplace, you're going to have a smaller level of significance because you want there to be less of a chance of discriminating. If it's not super serious, you want a smaller or a larger level of significance. I'm okay if I'm off by 10%, but you're going to be given the level of significance, so you don't need to choose any of that. You don't have to choose it. It will be given to you. Your alpha will be given to you. So, but if you were deciding to do hypothesis testing in your final project, just choose something. Just choose 5% or whatever you want to choose, 2.5%. I don't care what you choose. Just choose something. Just pick a number. Okay. So our test statistic, the test statistic is the z-score of your sample. So when you get your sample proportion, you're going to use that to find the z-score. That's what the test statistic is. Z-score basically of your p-hat. So we find the z-score of the p-hat. That is your test statistic. And so remember that this right here is standard deviation or standard error. So you just take p-hat minus p-naught and divide it by the standard deviation. And we use the p-naught in our standard deviation because we are assuming it's true until we have evidence otherwise. So our p-naught is truth until we have evidence otherwise. Just noticed my chat wasn't up. Any questions so far? Are we doing okay? I haven't made you do any math yet, so I'm hoping we're okay. Okay. So the critical value is the z-score based on your alpha. So based on your alpha, we get a critical value. And I'm going to show you where to get that and how to get that. It's not super difficult. We've done it many, many times. This area here out in the tails, that's not a good color for a highlighter. This out here in the tails is the critical region. If your test statistic lands in the critical region, that's when we fail the null or that's when we reject the null hypothesis. If your if your test statistic lands not in the critical region, it lands in this other place I'm going to highlight in the yellow area. If it lands here, we fail to reject. So this is reject. This is fail to reject. So this would be reject, fail to reject. Same thing over here. There we go. All right, moving on. So you just compare it. You're just, and I mean, this works. This is all great, and this is true. I like using the picture better, but basically, if your test statistic is outside of your confidence interval, so if it's less than the lower z-score or greater than the higher z-score, then we would reject the null. So outside of that confidence interval. Okay. I already told you how to compute the test statistic. So with the p-value approach, we're just going to use the calculator function. You're going to use your test statistic, and then basically what you're doing is finding out the probability of getting your test statistic if the p naught was true. That's basically what you're doing. You're saying, what is the probability of, and if that probability is less than your alpha, then we reject. We are not going to use the z table for our p-value. We are going to use the calculator because just use the calculator. I have found that using the table is not quite as accurate for my open math's sake. Sometimes it works and sometimes it doesn't. The calculator works pretty much every time. So that's why I'm like, just go to your calculator. Don't worry, I'll give you the function. If your p-value is less than alpha, highlight this. If your p-value is less than alpha, you will reject the null hypothesis. Now, this isn't less than alpha divided by 2. It's less than alpha. So even if I have this, like this, and this is 2.5, and this is 2.5%, my alpha is still 5%. I just cut it in half to put it in either tail. Alpha is still 5%. So if my p-value is less than 5%, I'm still going to reject the null. That makes sense? Okay. And then you state your conclusion, and we'll get there. You've already seen what the conclusions look like, and we'll start to do that. All right. I think we're almost ready to math. We are. All right. So in 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults, 525 stated they did not trust the media. This is I think, like the old one that we did. At a significance level, so alpha is 0.05. Is there evidence to support the claim that the percentage of Americans that do not trust the media has increased since 1997? Okay, so if you were on the test, the first thing you would say, you would look at this and you would say, it does not say that this is randomly selected, does it? It does not say randomly selected. So if I was on the test, I would say, we're going to assume it's random. Or you can just say random not stated. Either one of those is fine. You can say random not stated, or you can say we are assuming the poll was random. But you need to acknowledge randomness, whether it says it or not, acknowledge it. Then we would do NP times 1 minus P greater than or equal to 10. And that would be NP. So it'd be, what is my N? 10,010 times 0.46 times 1 minus 0.46. Okay, what is this? It's 250.884. I think we're good. Okay. I think we're good at 25. That's greater than or equal to 10. And then you would state that 1,010 is less than 5% of all Americans. So you would just make a statement, say 1,010 is less than 5% of all Americans. You have now have taken care of all of your conditions. All right. So now I'm going to look for the critical value. My alpha is 0.05. I'm going to pop over to the Z table. I have that right here. At the bottom of my Z table, it's kind of cool. These are the most common levels of significance we use. This is at the bottom of the Z side of the Z table. So right here, I have 0.05. We think we're using a right-tailed test. So I'm going to use 1.645. Now, listen, on right-tailed tests, our Z-scores are always positive. On left-tailed tests, they're always negative. Two-tailed tests, you use the positive and the negative. Now, if I put 0.05 into my inverse norm, I'm going to get a negative value. I just need to know in my knower that it needs to be positive because this is a right-tailed test. So you need to just be aware a right-tailed test is always going to have a positive critical value. So my critical value, I'm writing it down before I pop over to that other screen. Is 1.645. All right. Go back. Okay. I'm going to calculate my p hat because I didn't do that yet. It's 525 divided by 1010. So this is approximately 0.52. I'm just going to make it 0.52. Okay. So now I'm going to calculate my test statistic. So remember, we're finding the Z-score of our sample, our p-hat. So we do 0.52 minus 0.46 divided by, and this is going to be really ugly. If you use parentheses well, you should be able to put this whole thing in your calculator, but if you don't trust it, it's okay. So absolute must, if you're putting the whole thing in your calculator, whoops, if you're putting the whole thing in your calculator, I'm going to change the color so you can see it. Parentheses around your numerator. If you put the whole thing in your calculator, you have to have parentheses around your numerator. Otherwise, you will get the wrong answer. Okay. 0.52 minus 0.46 divided by square root of 0.46 times 0.54 divided by 1010. 3.83 approximately. I definitely could have gotten that wrong. I don't know if I did. All right. Because my test statistic is greater than my critical value, we're going to reject the null hypothesis. So if I was to draw this, which I highly recommend if this confuses you, draw things. If I was going to draw this, 1.645 Z-score is about here. 3.83 Z-score is way out here. Probably even further out than that, but I don't have room. This right here is the safe zone. This right here would be failing to reject. That p hat is x divided by n, so it's the number of successes divided by the sample. Sorry, by the sample size. So I'll just write it down. I did 525 divided by 1010 to get that. That was my p hat. Right. So we are going to reject the null hypothesis. I'm going to jump to where it's all printed on the screen in a second, all the math, and then I'll show you what a conclusion could look like. Right. Show you kind of what I would expect. All right. So it says that it's a simple random sample, but I don't think it says that anywhere. It does not state anywhere that it's a simple random sample, but in my solution here, it says it is. It shows that the NP times 1 minus P is greater than 10. Sample size is less than 5% of the population. Okay, we're good there. This is all the stuff that I already said. All right. Oh, I forgot to write that part. Darn it. Don't forget this. You have to show this. I'm so sorry. I was so into the math. I forgot that piece. When you are doing it for your test, don't forget that. Show me the setup. Show me your null and your alternative hypothesis. Remember that the null is always an equal sign, always equal. And then this right here and this right here are always P naught. It's always going to be P naught, those two values. So my null hypothesis is that the status quo is true, that 46% they got originally is truth. That is my status quo, the null hypothesis. The alternative hypothesis is that I think that the proportion is greater than 46%. Now, I'm not trying to prove 52%. I'm just trying to prove it's greater than 46%. Our level of significance is alpha equals 5%. My p hat is 0.52. Here's my test statistic. All right. Since this is a right-tailed test, we're going to use the positive z-score, the positive critical value. This right here, if this is all you wrote, even though this isn't the conclusion that they give to me, if that was all you wrote in your answer on your test, I would give you full credit for that. This is telling me why we're rejecting the null hypothesis and telling me that we reject it. I want to hear why, and I want to hear whether you rejected it or failed to reject it. Now, if you want to go a little bit deeper and say, since the test statistic is greater than the critical value, there is sufficient evidence to show that the actual proportion of people with whatever this is, I can't remember what it was, is greater than 46%. Therefore, we reject the null hypothesis. If you want that many words, go for it. But this right here is completely adequate for our purposes. Tell me why and tell me whether or not you reject. So p-value approach. I'm going to show you on the calculator. Basically, it's approximately 0. So I probably could, let me see. Let me look at my Z table. If I see the 3.83 is not even on my Z table. If it goes to 3.4 and it's not even on my Z table. So 3.49 and I'm at 0.9998. So practically a 0% chance of getting that p-value. I'm going to show you in the calculator in a minute. Don't worry. And you can see. Actually, I should show you right now. Let's do the conclusion and then I will show you. There's sufficient evidence at the alpha equals 0.05 level of significance to conclude that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1996 or 1997. This is good, but remember, I want you to tell me why. Tell me why. Tell me why. Oh, sorry. This is Kleist after she's been back to work for a week. All right, let's go to the calculator. I'm going to head back to the actual problem. Okay, the calculator will not give you a critical value. Just letting you know. The calculator doesn't give you a critical value. It will give you your it'll give you your test statistic and it'll give you your p-value. Thank you, Andrea, for the laugh. I love it. All right. So I'm going to go to the calculator. Here's my lovely calculator. We're going to go, because this is a hypothesis test, we're going to go to stats and then go over to test. We're going to go down to number 5, one prop Z test, because this is a one proportion Z test. Let's go down here. Put in the P naught. This is the original value that they gave us. This is the P naught, 0.46. Our successes were 525. And our sample size was 1010. Okay, and I'm going to tell you, I almost always choose the wrong one of these. I almost always choose the wrong one. You'll know if you choose the wrong one if you get something like 99.9%. So if I get a value that's too big, I know I chose the wrong one. So I'm thinking that it's probably this one, and I'm probably wrong. Uh-oh. Go over there. Because this is saying that I think it's greater than P naught. I think that should be the right one. I almost always choose the wrong thing. Nope, I chose the right one. Okay, so here's my Z-score. This is your test statistic. This is really close to what we got, but remember, they don't round. Since they don't round, this one's more accurate. We rounded our P naught or our P hat, so it's not quite as accurate because I rounded my P hat. This is still 3.8 something, and so it's still going to be basically 0. Remember, a proportion or probability cannot be greater than 1. So if you have something like this with this E-5 on the end, this is scientific notation. This means that you take this decimal, you move it 5 places to the left. I'm going to go to my p-value screen and write it down because I can. 0.123486. Okay, so once I write this down, this is what it would be. Took this decimal and I moved it 5 places to the left. So this is our probability right here. So the probability of getting a sample that looks like that, given that my actual proportion is 46%, this is that probability. That probability is basically 0. That's practically 0. So because this value right here is less than our alpha, because remember alpha was 0.05, this p-value that we got is less than alpha, therefore we reject the null hypothesis. Makes sense? So on the calculator, I can either compare this z-score to my critical value, or I can compare this p-value to alpha, or whatever the MyOpenMath tells you to do. On your test, I'm not going to choose for you. You choose. You get to choose which one you do on your test. I'm not going to choose it for you. This also gives you your p-hat. Questions? Feeling okay? Feeling groovy? So remember, going back here, oops, back to my tables. On a two-tailed test, you are cutting your alpha in half. That's why this is different. But you still compare your alpha to your p-value and not the p-value cut in half. So remember that. All right. That's 10.2. That was it. But if you have a question before we go on to 10.3, I would like that now. Or you can ask it later. Okay. We are now in 10.3. If you keep track of that kind of thing, I would like you to take all of the proportion information and I want you to stick it in your pocket. And we'll recap at the end. So we are using t-distributions because remember, with our means, we're using t-distributions. And a lot of that has to do with the variability of using a sample standard deviation. So once again, we're going to use t-distributions. So our critical value with t's, we are going to use n-1 degrees of freedom. However, this right here, this is a t sub x bar. When we are calculating like a z-score, but a t-score, given our sample, you're going to use the number of your sample size. Like this right here. Remember, this right here is the new standard deviation. So you take the mean from your sample, subtract it from the population mean that they gave you, and divide it by your new standard deviation using your sample standard deviation. This is going to give us our test statistic. Whoa, that was not a pen. This is how we'd calculate the test statistic. And our critical values, I believe we're using the t-scores, aren't we, for our critical values? I might have just lied to you. Hold on. Wait till I get there because don't trust me for a second. Okay. T-distributions, I'm not even going to go into how they're different. It's insignificant here. Okay. Okay. So the first thing we want to do, this is the things that you need to do on your test. These are the things that you are going to check on your test before you do the math. Simple random sample. If it is not a random sample, just say that it's not stated or that we're assuming random. So we want to determine whether or not it's normally distributed. It'll either say it's normally distributed or if our sample is larger than 30. Even if neither of those things are true, you can say that it's not normal and it is less than 30. So we can't assume it's normal, but you still do the math, okay? So I want you to talk about whether or not it's normal. So if it states it's normal, then it's normal. If it doesn't state it's normal, but your sample size is larger than 30, then you can call it normal. Okay, those are the two things that make it normal. Then the independent, this is the sample is less than or equal to 5% of our population. Those are the three things you want to check before you do the math. I want those on your test. Those are part of the process. Okay, now that we've done that, you're going to need to look and say, hey, is this a left-tailed, a right-tailed, or a two-tailed? It's the same thing we did previously, but you're going to have mean instead of proportion. So it's the same thing. I mean, if you did 10.1's homework, then you've set up plenty of these hypothesis tests. You just haven't done any of them. So if you already did 10.1, you're ahead of the game. Test statistic right here. We are not going, as I said, we are not going to, you use the actual sample size. I'm going to write that down there. Actual sample size. Don't use n-1 degrees of freedom here. All right. These are our critical region. This is the same stuff. The same rules apply here that we just did in 10.2. If it lands in the critical region, yes, so we are going to be doing t-scores for our critical values. I don't know why I was questioning myself. So if it lands in the critical region, you reject the null. If it lands inside your confidence interval, you fail to reject. This is the same thing as with proportions. It's exactly the same. I love it that the rules don't change from 10.2 to 10.3. I'm glad that like the way you determine whether it's you fail to reject or reject is the same. That would be so confusing, wouldn't it? If we like, hey, we're going to change it all up. Not that they don't do that to us occasionally. Okay. Compare your critical value with the test statistic or compare your p-value. Okay. All right. We're gonna do the math. This is gonna help. Okay. If your p-value is less than alpha, then you reject the null and then state your conclusion. You have to use your calculator for the p-value here. Using the table is not as accurate. The t-values, it's a lot more complicated. So just use your calculator. Okay, so this says this procedure is robust. Slight departures from normality isn't going to be a big problem. It says that if you have small samples and you're not a normal population, you shouldn't use this. But for our purposes, no matter what I give you for the test, just use it. Okay. We're assuming the resting metabolic heart rate resting metabolic rate of healthy males in complete silence is 5710 kilojoules a day. Research measured the RMR of 45 healthy males who were listening to calm music. Since it's 45, we can call it normal. Calm classical music, they found their average RMR to be 5708. 0.07 with a standard deviation of 992.05 at an alpha equals 0.05 level of significance. We want to know if it is different. So different. This is a two-tailed test because it says different. Two-tailed. When it says different, it's two-tailed. I am going to find my Okay, so first thing, it doesn't tell us that they're randomly sampled. We are going to assume random. That's the first thing we check. The second thing we're going to check is it normal? Because we have a sample size of 45, that makes our sampling distribution normal. So based on our sample size, it's normal. Last thing, is it independent? How many? 45 males? 45 is less than 5% of all healthy males. So we can assume independence. So those are the things I tested. Next, I'm actually going to set up my hypothesis test. My null hypothesis is that mu equals 5710. My alternative hypothesis, do we use one? No, okay. Is that the mu is different than 5710. Give you a second because I'm going to bop over to the t-table in a minute. Okay, let's bop over to the t-table. Because some of you don't have inverse t, I'm going to use the t-table. We don't have a 44. Our critical value, we would use 44, but we don't have a 44. So what we're just going to use the critical value halfway through. So since this is a two-tailed test, we're going to use 0.05 divided by 2, 0.025. We're going to use 0.025 to find our critical value because this is a two-tailed test. So I'm going to pop over here. 0.025 is right here. So I'm going to scroll all the way down. Okay. What I'm going to do is I'm going to find, because this is 50 and this is 45, this is 40, and we really want 44. but it's going to be close enough regardless. I'm going to take 2.021 plus 2.009. I'm going to divide that by 2, and I'm going to get a critical value. My critical value is halfway between those 2 points. I use 2.015. I'm sure inverse T would back me up on this at least closely. I'm going to use inverse T real quick and see what it says. It's going to be really close. So I have 0.05 degrees of freedom, 44, because we use n minus 1 degrees of freedom. Unless it's a big number, use n minus 1 degrees of freedom. Otherwise, you're going to have to estimate if you're using the t-table. What the heck? What did I do? Oh, well, that's what I did.
Wouldn't it be 95%? Because it's the inverse.
Oh, I just know, the way that I do it is I just know that I need the positive and the negative. It doesn't matter. I'm doing weird stuff here. Okay, inverse T. Thank you, though. It doesn't matter. As long as you know I need both the positive and the negative, because it's, there we go. See, that's the same number I have. So our critical value, because it is a two-tailed test, we need plus or minus. I'm going to pop back over. We need plus or minus because if my test statistic is lower than negative 2.015 or greater than positive 2.015, we'll reject the null hypothesis because we're looking in the tails. If it was a right-tailed test, you use the positive no matter what your calculator says. If it's a left-tailed test, you use the negative no matter what your calculator says. Okay, got my critical value. Let us calculate our test statistic. I'm going to write this down. Okay, I'm going to use the mean that we have got here, 5708. Oops, what the heck? 08.07 minus 5710 divided by standard deviation is 992.05 divided by the square root of n, which is 45. Remember, if you put the whole thing in your calculator, you're going to need parentheses around your numerator. I would probably put parentheses around this entire thing also. Otherwise, weird things are going to happen. So if you put the whole thing in your calculator at once, be really mindful of your parentheses. And nobody's ever gotten in trouble for using too many parentheses. Okay, I got approximately negative 0.013. And draw a picture. So this right here is negative 2.015. Over here is positive 2.015. Our test statistic landed us right here, which is negative 0.013. This is the safe zone. If it lands in here, we fail to reject the null hypothesis. So it didn't land in the critical zone. It landed inside my confidence interval. Therefore, we fail to reject. So what this is saying is that if that it is likely that we could get a sample like this with our actual mean being 5710 kilojoules per day. So we could get a sample that looks like this if that is the true mean. I'm going to pop over to the other screen where it's all typed in there. Okay. Oh, that says we assume Let's see. We assume that it was, it doesn't say that it was simple random sample. I think it was supposed to. Okay. Sample size is large. Follow the steps for testing. Okay. So here's all of this stuff. They got the same test statistic we did. They wrote down level of significance. They wrote down their hypothesis test and all that pretty stuff. And they're showing that our test statistic is between the two critical values. Therefore, we fail to reject. So now let's use the calculator to check out the p-value. Questions on this before we do that? This is a good spot to stop and ask questions. Okay, let's pop over to the calculator. So what you're going to use for the means, for when we're using the t values, let's go to stat, over to tests, and you want to use t-test, which is your second option. T-test is what we're using. Hit enter. So once again, if I gave you a list of data, you would put that in your list, your L1 list, and you would just use data right here, and it would fill out all of this stuff for you, except for the original mean that they gave you. I think I have one of these examples. Let me look. I do. I have one of these examples, and we'll do that in a minute. But all they gave us is stats. They just gave us the information. So we're going to use the stats right there. So my mean, I got to go back, was 5710. The X bar, they gave us that. So the mean that of our sample, remember X bar is for the sample. The standard deviation of our sample, well, that's not what it is. It's 992.05. And our sample size. And this is different, so we're going to click on that one, the not equal to. This is the only one I get right consistently, is the not equal to. Now, this number is super close to 5710, so I think that in our brains, we probably could have said, you know, this probably is not going, we're probably not going to reject. So we're going to expect a pretty high p-value. Yeah, look at my p-value. Normally, if I had a p-value of 0.9896, I would question whether or not I chose the wrong thing. But you can see that the test statistic is almost right at the mean. We're not even a full standard deviation away from the mean. So this p-value makes sense. This p-value is obviously not less than our alpha. Therefore, we fail to reject. Questions before we move on? Okay. So I want you to tell me why. So whatever method you use, either tell me that your test statistic was between those two values, or your test statistic was less than, or however you explain comparing your test statistic to your critical value, or mention the p-value. Tell me how you know that we failed to reject, and then tell me that we failed to reject. This right here is somewhat vague. Yes, I can kind of read between the lines, but I want to see the words. I want to see these words right here. This right here is perfect. This is a perfect way to answer this on the test. The p-value is greater than the level of significance. We failed to reject the null hypothesis. Tell me how you know, then either say the words reject or fail to reject. I want those words on the test. Make it really clear. Okay. All right. What I would like to do on this one, what I would like to do is just use the calculator, However, we do need to find, we're going to need to set up our hypothesis test, and we will need to find our critical value. So let's start by setting up the hypothesis test. So this is, according to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different from 5.67 grams. He randomly, look at that, randomly selects 18 state quarters, weighs them, and obtains the following data. All right. This is a simple random sample. He tells me that he randomly selected them. They did not tell us that they're normally distributed, and our sample size isn't large enough for us to assume that it's normal. However, we are still going to use this method. So you would need to state those things. 18 quarters is obviously less than 5% of all of the quarters. So we're going to go to our calculator and go to stat edit. I need to clear this out. And I'm just going to enter these values in. Hopefully I'm going to do it well. No typos. Oops. That's 18. Give y'all a second to make sure you have them all in there, in case you were following me. Right. So now we're going to go to stat, over to tests, and down to t-test. We're going to do data because that's what we have. And our mean that they gave us is 5.67. And list 1 is where our lists are, and leave frequency at 1. Now I'm going to go to not equal to because the word that we got was different. So this is a two-tailed test. It is a two-tailed test. I didn't get my critical value yet, but that's okay. All right. So I'm just going to let this sit here for a moment. Actually, let's take a look real quick. My test statistic is 2.75. My p-value is 0.0135. Already we can tell that we're going to reject the null hypothesis because this p-value is less than the 5% that our alpha is. Alpha was 5%. This p-value is less than 5%. So obviously, we're going to reject. But I'm going to go to the tables real quick. Once again, we're going to do 0.025 because it's a two-tailed test, and I had to cut that alpha in half. We're going to go down to 17 because remember it's n minus 1 degrees of freedom. So my critical value, whoa, that was weird. Okay, critical value. Critical value is 2.110. 2.110. I wrote that down right there. So back on my calculator, this right here, this value right here is greater than 2.110. So this would be outside of that confidence interval. It's in the critical region. Yes.
I'm so sorry to interrupt, but I'm having a calculator problem. When
Okay.
I put all the stats into edit in the list one, and then when I went to test to t-test,
Mm-hmm.
it's it won't it only has from like when I go into data,
Uh-huh.
it still has the 5710 from the previous thing, and it isn't putting the new L1
Oh,
and
you have to put this in. This is the mean that's given in the problem.
oh, sorry.
No, no,
Sorry,
don't
I'm
forget it.
panicking.
No, this is the one you have to
Oh,
put in because this is the one we're comparing it against. It doesn't know this one.
oh, okay, thank you. I
This
was
is,
just
yeah,
checking.
this is what we're trying to, this is my null hypothesis right here.
Okay, great. Thank you.
Uh-huh. I haven't written my null hypothesis yet, but I should have already written it. I'm doing things backwards.
Okay.
Okay, so yes. Okay, now I'm confused. We're good. Okay, so we got a test statistic. So the T sub whatever is, was it 2.75? That is greater than my critical value. I'm going to write the null hypothesis and the alternative because I didn't. I'm being lazy and I'm sorry about that. I need to not be a lazy teacher. So we're assuming it's 5.67. We're testing whether it's different than 5.67. So because this is greater than the edge of my confidence interval, which is at 2.11, we are going to reject the null hypothesis. Now, if this was negative 2.75, we would also reject because this really is a plus or minus. Because it's a two-tailed test, if it was less than the negative number or greater than the positive number anywhere in that critical region, we would reject. Other questions? I should write down that p-value also. P equals 0.014. I'll just write it like that. So, and this p-value, since this p-value right here is less than my alpha of 0.05, we reject the null hypothesis. Those are the two ways to compare. So on your test, if you state either one of those things, I don't care which method you use, state one of those things. P-value is less work, but I kind of the thing I like about using the test statistic and the critical value is that I can picture the curve and I could picture where they're landing on the curve. That's why I kind of like those. And your homework will have both. It'll have p-values and it'll have critical values and test statistics. It's going to do both to you, but you're going to get to choose because out in the world, if you were doing this for whatever reason out in the world, you could use whatever method you want. Okay. So I already said all of this. So, um, out in the real world, if you had a small sample size like this, you would, unfortunately, as much as you would hate to do it, you would either create a box plot or draw a histogram to see if it's normal. I'm not going to make you do that. I'm not going to make you create a box plot or a histogram. I just want you to tell me that it's not normal or that you don't know whether it's normal. Just want you to acknowledge that that sample size is too small. You don't have to actually graph it, but that's what you would do right here. You would actually graph it to determine that it was normally distributed, but don't worry about that. Okay. This is what the graph looks like. And this is a weird graph. I don't know why they use this one instead of a box plot or a histogram, but you can see that it's all kind of clustered around the line of best fit. It has the R value is pretty high. Because the R value is pretty high, we're assuming it's good. Okay. Here's my I like this one better. This is the box plot. There's no outliers. It's a nice, pretty normal box plot. Okay. This is all the stuff that we just did. It's nice and pretty and typed up for you. And then the same thing. P-value is less than the level of significance. We reject the whole hypothesis. This is 100% okay. 100% okay to make that your answer, or 100% okay to make that your answer on your test. Either one of these. Tell me why, and then reject or fail to reject. So that is it for the lesson. I'm going to do the recap in a second. Before I do the recap part, does anybody have any questions? All right, let's jump into the recap, and then if anybody has questions. Well, that wasn't it. I thought I had a recap. I guess I don't have a recap. Okay, I'm going to pull up that. I thought I had a recap on there. It was on there before, but I think I must have. So here's the handout right here. So, this shows me the things that you have to assume. This is why I said this is a good thing to print. So for random sampling, for our mean, they'll say random sampling, then you check these things. So you check normal and you check for proportions. This tells you if it's normal. This tells you if it's normal. Establish your null hypothesis. And for some reason, it isn't showing up correctly on mine. I hope it shows up better on yours. This is like, oh yeah, no, this is what it is. Greater than, less than, whatever. This is all of this. Left-tailed, right-tailed tests. This shows you how to calculate your t-test or your test statistic, and it tells you the calculator function. And then p-value is just with the calculator function. And then this tells you whether to reject or fail to reject. This is a pretty good handout. I'm also going to jump to my PowerPoint that I have right here. I could have opened the one I'd already downloaded. On the second page, this shows you everything. Yes, you can use Binom for your p-value, but I don't recommend it. Just use one prop z test. And it tells you all of the only thing it doesn't give you is the things you have to check ahead of time. So make sure that those get in your notes, the things you have to check ahead of time. All right. We are still recording. So now is the time to ask questions while we're recording. Okay, I'm going to turn the recording off.